All right. So just to remind, we mentioned that we have been using single pixel cameras in the field aperture cases, and the painful raster scanning is a very laborious way of making images. We can do something better, and instead of ideally, what we require is to build a big telescope to study the sky at very fine resolution at radio wavelengths. It's a daunting task, almost impossible to get the same kind of resolution as our eye has at optical wavelengths. If you translate that, the same lambda by d, where lambda has increased by orders of magnitude, you will find you will require a 10-kilometer radio eye to get similar resolution that we are used to at optical wavelengths with our human eye. Now, such a telescope cannot be built as single piece or steered and so on. So what we do is we, instead of making measurements in the angular domain, we try to make measurements in its Fourier domain. So these can be understood at holographic measurements. It's like measuring Fourier components of the distribution of the sky. We can easily imagine any distribution. In this particular case, bright intensity distribution in the sky can be thought of as superposition of large number of sinusoidal patterns. And if we can measure each one of the sinusoids with its amplitude and phase, we know that we can reconstruct the picture by superposition of such things. It turns out that each one of these sinusoids and its amplitude and phase can actually be measured. And that measurement involves using a pair of antennas and asking how similar the signals received by the two antennas are. Formally speaking, we look for mutual coherence in the signals that are received in the two locations. And this amounts to actually measuring one Fourier component or one filtered sinusoidal pattern in the composition of the sky. It effectively amounts to multiplying the sky brightness by a sinusoid and integrating over the sky and getting one number, which is a result of this product and integration. As you have seen, this we will relate that to a Young double slit experiment where you know that you will see a fringe pattern. So the fringe pattern is exactly equivalent of this sinusoidal pattern I'm referring to. Now you can ask how many pairs you can get. Somebody gives you n antennas, you can get NC2 independent pairs. So you can make n into n minus 1 by 2 measurements of the Fourier components. By ensuring that you don't measure the same Fourier component twice, that means avoiding redundancy, you can cleverly arrange your apertures or sensors in a way like in this example, or in the case of GMRT, you can arrange them in an optimal way, such a way that each pair of antennas measures a different sinusoidal pattern with different orientation and different periodicity. So by doing that, you can measure large number of Fourier components. You can also use Earth rotation to measure different situations, even with a single pair of antennas. Because if you put the pair of antennas along the east-west, for example, as the source rises at the horizon, it will see the line joining the two antennas as simply a point. So you have made it appear like a separation which is zero. It's only when the source comes overhead that it sees the fuller extent of the separation between the two antennas. So you can, using the same pair of antennas without moving them, using the source direction change, you can make measurements as if you made measurements with different separations between the two antennas. You can also imagine that if there is a source at the pole, it would see the separation, the line joining the two antennas rotating with respect to its nose. Suppose the source had a face and a well-defined axis defining its nose. you will find that the line joining the two antennas on the Earth will appear to rotate with respect to the nose of the source. And so you will find that with one pair of antennas in the east-west direction and source rising at low declinations, you will find that you have actually made measurements along all the measurements that you would like to make along a line. In the other case, with the tip of the vector joining the two antennas, making a rotation that a source at the pole would see, you have made measurements that you would like to make along a track, which is a circle. For any in-between case of source direction not being at the pole and not being at the equator, and your antennas also not being separated exactly along east-west or north-south, you will find that the typical track of the measurement you do of this vector separation will be along an ellipse. So you can get, by using Earth rotation, measurements along an ellipse, and such ellipses put together might fill all the information space that you would like to sample. I'm describing these in words. We will look at pictures relating to this pretty soon. And this way we can get all the information in the Fourier domain corresponding to a big aperture, and then use Fourier transform to translate that back into the image. Without going into all these details, we can ask also a very simple question where, imagine a big dish made, a fictitious dish made. We can ask what we are receiving at the focus of such an imaginary dish. We will receive information which is coming from different small sub apertures which constitute the big aperture. Let's label them as E1, E2, E3, E4, up to En, based on the n pieces that we want to consider for this illustration. So big aperture made of n small apertures is what we are looking at. We know that the electric fields that we have in these different parts of the wavefront that we receive are brought to the focus, and we get the sum total of this. What we are interested in is the modulus square of this electric field, and that amounts to multiplying the total electric field, or the signal that we receive proportional to the electric field, multiplied by its complex conjugate. So from your simple maths background, you will know that this product, where individual E total itself is a sum of large number of E's, and multiplied by its complex conjugate, you will find it can be expanded, and you will find all the description of this expanded version can be described in terms of pairs of cross terms. Cross terms which are multiplication of EI times EJ, I running from 1 to n and J running from 1 to n, EJ star. Essentially, you will find that the measurement that you wanted to do can be expressed in terms of sum of products, pairwise products of electric fields received by different pieces of antennas. Now, this is exactly what a two-element interferometer would measure. So you require a large number of two-element interferometers to measure all the possible terms in this, and when you sum them together, you will get the intensity that you are looking for. But having measured these pieces separately for sub apertures, you have the advantage that you can add them in with different phases also, and that would amount to getting the electric field associated with another direction. And this way you can, using the sub measurements of these products and putting appropriate phase shifts before combining them, you can make the instrument look in different directions. And this is how we can make images, by making these pairwise measurements of electric field products. So this is what we're going to illustrate. There are many telescope arrays, which are the first such big one was the Very Large Array in New Mexico. We have now geometry. So essential point here is in this what is called synthesis imaging. What we are doing is synthesizing the aperture, a big aperture, by using small apertures and using them cleverly to make measurements which are component measurements in the big measurement that we want to do and add them together. The essential assumption in all this is that the sky distribution that we want to study is not varying in time. And this assumption helps us to make some parts of the measurement now, some parts of measurements tomorrow, some parts of the measurements day after tomorrow, and combine all that together because they correspond to the same brightness distribution that we wish to look at, and we can assume that it has not changed from today to tomorrow and so on, or even routinely that we do within a day, it has not changed. So with this essential assumption, we can measure the similarity between the signals received by a pair of antennas, which might be separated by different distances from and with different orientations. So each one of them, when we measure the similarity, we note down that number. And that measure of similarity is what is plotted here. So starting from the center where the separation is 0, for any other pair that we're going to consider away from 0, we will have a specific orientation. So if the pair is separated like this, and we measure a certain similarity between the signals received by the two, we note down that and mark a point here. And same way as is done here. And so we can fill this space. If we fill this space to the level which is labeled in units of wavelength, so suppose we measure it to 100 in units of lambda, we have information over that extent. Inverse of that scale defines the resolution that we will get. So we can go and fill this information up to whatever is the extent of the separations we can achieve, which in the case of GMRT can go up to 25 kilometers. We will have information filled in this domain. And then all that it requires is Fourier transform. So Fourier transform this information and you will get the image of the sky. So because you could not measure this directly with fine enough resolution because you didn't have a telescope like this, we used the description of it in the Fourier domain and asked whether we can measure that. And that became measurable with a large number of pairs of antennas, and including you exploiting the rotation of the Earth to see the same pair as in different orientations and different separations, allowing us to make measurements of different points in this plane using the same pair. In all this, we are using some concepts which, as I said, we are measuring the similarity between the signals. And really what we are trying to measure is the coherence in the signal. Coherence, many people understand just as, described as two things are coherent if their phase difference is constant. That's the definition many people tell me. But it's much more deeper than that. Correlation is a technique to find similarity between the signals. Many times, many things that might appear dissimilar might still be coherent. But if they are incoherent, we are certainly going to find no correlation between them. So you will find that lack of coherence would lead to lack of correlation. That means there won't be any similarity between the two things if they happen to be incoherent. But the converse is not true. So while we are trying to look for coherence in signals received at the two locations for making these pairwise measurements, we need to remember that while the correlation might be formally small, that is not the full story. We should look for possible effects that might make things look somewhat different, but if certain things are accounted for properly, they might be actually same, and they might be then showing high degree of correlation. And I will give you a very simple example of it. When particular two observers looking at the same source, one in Australia and one in India, looking at a source which is setting in Australia. I think if it's setting in Australia, it might be overhead in India. So you will see the Earth rotation vector is now perpendicular to situation, the direction that we see in India, whereas the telescope in Australia is moving away along the line of sight of the source. And so you will see Australia observer will see a Doppler shift in the signal that is received. So even if a single tone was radiated by the source, you will see a Doppler shifted version of it, whereas the Doppler shift for an Indian observer would be 0 because it's moving tangential or direction perpendicular to the direction of the source. And this would now lead to two sinusoids which are at a slightly different frequency. And if you compute a formal correlation between this, you will find that the net integral of the product of those two sinusoids is 0. So you will find that you should not blindly throw away that as saying there is lack of correlation and that implies lack of coherence. You would have to do the right things to bring them to the same level so that the comparison is fair. So you have to account for all these effects that might change the appearance of the signal. In this particular case, I gave the example of the Doppler shift. They might be simple things like they might be even locally two antennas looking at the same signal might have, one of them might have some phase shift of 90 degrees and two sinusoids with 90-degree phase shift will show no correlation formally. So what you need to do is account for that phase shift and then slide one over the other and then compare. So while assessing mutual coherence, you need to be mindful of all the scalings that you need to try or account for and any translations. Now, while in time I just described the scaling with a phase shift amounting to a shift in time, you can also think of the Doppler effect compensation as a translation in frequency. So scaling in both the time domain as well as in the other domain, its Fourier domain, have to be taken into account. In general, two things are mutually coherent. If I make a copy of it, copy of a given description in phase space and then make any modifications to it which are reversible, then you will find the coherence is still not destroyed. But if I do any translations or mixing which is undoable uniquely to get the original description in phase space, then I have destroyed the coherence. So you will find the mutual coherence not destroyed through any reversible translations or operations. So what we have is the analogous situation that the pairwise measurements that we want to do are exactly synonymous with the Young double slit experiment that we perform. You will find that the two apertures that we will use in radio, they are also used in optical to make measurements of the source signal. Here they are made to interfere and you see something on the screen. But in radio, we sense the electric field associated with the electromagnetic radiation received and then make comparison between the two by taking one and multiplying by the conjugate of the other. So this is what we are trying to do. We are trying to synthesize an imaginary big telescope by using pieces of the antennas which will correspond to sections of this imaginary big telescope. Of course, one has to be mindful of the effects that I said which might appear to destroy the correlation. One of them is simply that if there is a source at some angle with respect to vertical, these two pieces will receive the same wavefront at not at the same time, but with time shift, or after having traveled some extra distance, which depends on the angle, some trigonometric function of the angle, and the length of the baseline, as you say, of the separation between the two antennas. So ideally, we need to account for this by delaying the signal that we receive from here, where the signal had arrived earlier, so that the patterns match if they happen to have matching. It's the same thing. I've just written the expression d sine theta is the extra part difference, and we want to be on the equiphase surface, which is the wavefront at both the locations. You will find that you will get, when a pair of antennas is used, and you simply make a sum of the voltages which are proportional to the fields received at the two locations from a discrete source, you will find that you will see fringes at any given frequency, which is basically described, one such sample is described here, because it is going through ups and downs of the interference pattern associated with the combination of the fields received from the two. Based on the relative phase differences, you will do a constructive or destructive interference of the fields received, and that is what will show up in the sum of the contributions from the two. It will also be not same identically at all the frequencies, because phase difference depends on the frequency. The delay, physical delay might not is independent of the frequency, but the way it will shift the phase at different frequencies will depend on frequency, and that's what will change at any given time. You might find that it's a constructive interference at some frequency, but it's a destructive interference at some other frequency. So you might see tilt of these fringes seen in the what is called the dynamic spectrum in the frequency versus time diagram, where the equipment is kept looking up and the source is passing over it due to the Earth's rotation. You can see the fringes like this with smaller separation in time or in angle when the baseline length is long. You will find sparser fringes when the baseline separation is small. So when these are longer baseline, faster variations in angle. These are smaller baselines, smaller separations, and slower variations in angle. So you can basically measure the intensity of these fringes and associate that with the Fourier component that you wish to measure in order to synthesize a big aperture. So you can have large number of pairs. Typically, you will with a large number of pairs of antennas that you can construct using an array of like this. In the case of GMRT, you will see one of the baselines will make measurements along all these points of, which are representing the separation in kilo wavelength along X and Y direction, which are labeled as the UV coordinates, the spatial frequency coordinates. So you would have made all these measurements during the 4 hour that you might have to look at the source. If you take baselines for a given antenna with respect to all other antennas, then you might get 29 baselines given the total number being 30 antennas, and you would have sampled at any given instant all these points in the Fourier domain. With 4 hours spent with one antenna with all other antennas making pairs, 29 pairs, you would have made measurements along these tracks. So it is like wanting to fill this entire area with measurements with a sketch pen which can draw ellipses or parts of the ellipses, and many strokes can be made based on the number of pairs you can have. And so you can make large number of strokes to fill this area. You can see that more and more strokes you can make, more and more area you can cover. And if you are taken care not to make a stroke over the same existing stroke and so on, you will avoid wasting your effort and rather use that effort in filling other space. Each one of these measurements, if you take data from individual baselines, individual spatial frequency component, and begin to put that in the image, and that is what you do when you take Fourier transform. You take each point and associate a sinusoid with respect to that, and put that sinusoidal pattern in the other domain, and keep superimposing these patterns to get a complete picture. And so what you'll find is in the right ascension declination in the angular coordinate, you can take a particular baseline and put the pattern associated with. What you have done is the earlier measure of level of similarity between the signals is used to scale the amplitude, and the complex information, the complex visibility that you had measured also had phase information. So the way the phase shift of this pattern has to be arranged is known. The orientation of this pattern is decided by the way the baseline, the line joining these two antennas was oriented. It was oriented this way, and so the pattern will be in that direction. So having put this pattern over the patch of the sky that you want to study, because you had this measurement, you knew the amplitude, you know the phase, and the orientation of this pattern, you can keep on looking at different baselines, and you will find that they give you different patterns. When you begin to combine this together, you will find the picture emerging as a result of the Fourier transform, and this is the picture you'll get. Of course, this looks, although this is a nice bright source which stands out well above this other junk contribution, you will find that this junk still physically exists, and it is a result of you not having made all the possible measurements that you would have wished to make. And it's a result of that inadequacy, which you can account for using appropriate techniques called clean, and you can get a beautiful image of that piece of the sky. In this particular case, it happens to be a nice compact source. It will never appear like a dot, a point. It will have a finite size in angle, and that angular size will be now effectively the inverse of the effective aperture you have built through these measurements. So if you have synthesized an aperture by using these pairwise measurements over 25 kilometers and you're working at 1 meter wavelength, you will actually have 1 upon 25,000 radian in, as an angular resolution in radians. And so that's a very impressive way of doing it. So as I said, interferometers have a nasty point spread function. These responses, which are a result of having measurements only at certain locations in Fourier transform, this windowing pattern results in a response which has not just one individual peak that you would have liked to have at of certain finite width associated with your resolution, but it also has lots of side lobes and ups and downs around. One can deconvolve this. What happens is for every point in the image, you have this replica of the point spread function pairing scaled by the intensity of that particular source. And so effectively, it's a convolution of the true brightness distribution with this point spread function. So you can use deconvolution techniques, which are not always trivial based on the complexity of the field you're looking at in terms of its intensity distribution. So this is another example of if you happen to have field measurement set, which fills this UV plane spatial frequency domain in this fashion, you will get a reasonably good point spread function, which is has a very tall peak here, but has finite amount of artifact around, which you need to account for. You cannot imagine, you cannot infer that this is a new source that you have found in the field. Even if there was only one point source, you might see these additional responses which have to be attributed to this, and only after doing that you can see whether there is any another source or another intensity feature. Each one of the baselines is capable of measuring over the 6 hours track, measurements along a track, which are typically along an ellipse. In general, the line being a spatial case of an ellipse and circle being the other extreme case of an ellipse. So our idea is to use large number of felt pens and draw tracks with them. We are allowed to. We can also use thicker felt pens to fill this. And what is a thicker felt pen will amount to? Remember that each one of these tracks is at a distance, the lengths, the distances from the center are measured in units of physical distance divided by the wavelength. Now, when we are using a finite bandwidth, we are looking at different wavelengths, no matter how small separation they might have. And you will find that the same physical separation will amount to different spatial frequencies corresponding to different frequencies, the temporal frequencies. Because the lambda is different, the same physical length d will amount to slightly different d by lambda at different lambdas. That can be used to gain certain thickness for the felt pen that we're going to use to draw these tracks. When that aspect is used, it's called bandwidth synthesis. The aperture synthesis is benefiting from using large number of antennas, which allow us to make NC2 pairs. Each pair can measure a particular point in this plane. With Earth rotation, we can use the same pair to measure information along a track in the UV plane. That's called Earth rotation synthesis. And in addition to that, we can use the dimension of finite bandwidth, where we use information at different wavelengths, closely spaced, which allow us to, at a given point, measure information along the radial direction. Different points will be measured across the bandwidth. So it's like using a thicker felt pen. When all these three things are put together, you have done aperture synthesis using Earth rotation and the dimension available along the spectral width, which is called bandwidth synthesis. So you can benefit from all this and make as many. So you know that VLBI is also routinely used these days, where you can synthesize a Earth-size aperture and get resolutions corresponding to what you would get if you had a telescope of that size, going down to milliarc seconds routinely. All of you must have been seen this news in the recent time using the Event Horizon Telescope, which imaged the black hole at the center of M87. So it was possible due to this technique. You can also see how using different telescopes, you can study scales, details of the source on different scales, and using different frequencies with the same instrument, how you can refine your ability to see the details with the clarity. And you can see the hierarchical zooming here showing fascinating details at the level at which you would not have imagined with normal equipment. So the quest for bigger and better and more sensitive instruments to probe deeper continues. Multi-wavelength nature of probe is now more implicit. Earlier people used to say, I'm a millimeter wave astronomer, I'm a decameter wave astronomer, because they had instruments which were focused on those frequency ranges, and they were largely busy collecting some information now. But after having information about sources at various frequencies, to understand a particular object, you require the entire jigsaw puzzle together, all the pieces together in the jigsaw puzzle to understand the mysteries about the sources. So it has become a multi-wavelength pursuit, and it has now even been extended to multi-messenger. You are all aware of the square kilometer array, which in your times will be a fun toy for you guys to play with. Of course, in doing all this, you have to be aware of contaminants and the signals that do not come from the sky but spoil the fun while looking at